All right. Now, the topic for this lesson is integration of even and odd functions, but actually that's the second half of this lesson. The first half of this lesson is a continuation of the last lesson because we dealt only with indefinite integrals in that lesson, and then the theorem that I gave you dealt with definite integrations. So we're going to do the same thing we did last time, only with absolute endpoints of A and B. And we'll do one of those, and then we'll do a couple of these right here. So it's basically the same thing as what we did last time. So on page 306, turn to problem number 93, and this is the problem we have right here, is that we want to find the integration from 0 to 4 of x over the square root of 2x plus 1 dx. Now we need to rewrite that right away. We need to get rid of this radical in the denominator and make that a radical in the numerator of the negative sort. And of course that's going to be x times 2x plus 1 over the negative 1/2 power dx. Now, again, we're going to use the chain rule here. We're going to replace the 2x plus 1 with a u to make it much simpler in comparative terms. That means then that du is going to be the derivative of u, which is 2. So this is going to be 2 dx. So what we're going to have to do next is rewrite this in terms of x and rewrite this in terms of dx. And so for this one right here, we subtract 1 and then divide by 2. We get x is equal to u minus 1 over 2. And for this here, to get dx by itself, we divide by 2, so dx equals du over 2. Now we go in and substitute for all that. So that means then that x, we said, is u minus 1 over 2. That's our x right there. We're going to put that right there. And this is, by definition, u to the negative 1/2 power. And we said that dx is equal to du over 2, so we'll put du over 2 there. Now, you notice you have two 2's in the denominator. They're all multiplying. And there's nothing in the numerator, numerically speaking. So that's a fraction 1/4. And I put that outside and just dealt with the non-numbers, if you will, just the variables here in the setup for the integration. So we have 1/4 in, and then what I'm going to do here is distribute this u to the negative 1/2 across here, and it gives us u to the 1/2 minus u to the negative 1/2 du. And then we are going to start integrating from 0 to 4 for this. We're going to get the integration value for this first in terms of u, and then we're going to substitute in the x values that we had determined at the very beginning, and then go from there to substitute for x. So that means then that we're going to have 1/4. This is 1/2 here. Increase that by 1, you get 3/2, so the denominator has to be 3/2 and the exponent's 3/2. We have our 1/4 in front, like I was trying to say, and I cut myself off. It's so rude of me to do that to myself. Anyway, so then we add 1 to this. This gives us a positive 1/2, so we put 1/2 in the denominator, and that gives us that. And again, we're going from 0 to 4 on this, eventually. Next, we do our little manipulations here. I have to take the reciprocal of 3/2 and make that 2/3 here. Reciprocal of 1/2 and make that 2. So that gives us 2u to the 3/2 over 3 minus 2u to the 1/2. All right, at this point then we're going to plug in, let's see here. Oh, so I have to distribute the 1/4 across both of these. Sorry about that. Yeah, distribute the 1/4 across this. When I take 1/4 times this, the 2 and the 4 cancel out, leave me 1/6 u to the 3/2 power. And I distribute this 1/4 over here. The 2 and the 4 cancel out, leave us 2 in the denominator right here with the u to the 1/2 on top. And again, we're going from 0 to 4 on this. So I combine this into one fraction. Lowest common denominator of 6 and 2 is 6. So 6 goes into 6 one time. 1 times u to the 3/2 is u to the 3/2. 2 goes into 6 3 times. 3 times u to the 1/2 is 3 to the 1/2. So this is our fraction right here. We're going to factor out what we can to, so we have a u to the 1/2 at minimum in each of these. So I take that out, and I'm going to take out the denominator 6, so this becomes really clean to work with. So this will give me then u to the 1/2 over 6 times u minus 3, and then going from 0 to 4, and now we can plug in the 2x plus 1 for the u. And this gives us this right here, so the 2x plus 1 to the 1/2 power is this. The 2x plus 1 for this u is right here, and no, sorry, it's 2x minus, what did I, oh, here, 2x plus 1 minus 3 here, plugging that in here, and that gives me 2x minus 2 here, and I keep this right here. And that's just about as far as I can go with this. So now I can start plugging in numbers. So I'm going to take 4 for x for the entirety, minus 0 for x for the entirety, and subtract the 2, since those are the 2 endpoints. And this is just basic arithmetic at this point. You can follow along on your script there, but we should end up with 10/3 for an answer. Again, looks complicated, it really isn't. You just have to make sure that you account for every little nook and cranny, negatives, exponents, reciprocals, all that stuff going on in here, which is going to make you a much, much, much better math student when you master this, which is my goal for you, of course. Now the next thing I want to talk about are the even and odd functions. Now, I don't know how much you have dealt with even and odd functions. I'm going to assume that you don't remember very much, even if you did. Start with the theorem that's based upon this. It's the integration of even and odd functions, and it's basically saying that if f is integrable on the closed system from negative a to a, and that's really important, that f has to have a beginning and end point that are the same number, only on opposite sides of 0. And the reason for that is because we can split it in half and do half of it and then double it for the entire one if that is a necessity. Then it says if f is an even function, then the integration from negative a to a right here of f of x dx is 2 times the integration from 0 to a, what I was just saying, for f of x dx. The second thing is if f is an odd function, then the integration from negative a to positive a of f of x dx is 0. That's really easy. But you have to prove what is even and what is odd. So the question is, how do you do that? Well, it's funny you should ask. I just happen to have the answer. So this lends the question, how do you determine if a function is even or odd? If a function is even, then f of x equals f of negative x. Now what you do is you replace every x with negative x and see if you get the same thing. If you do, if you get the same basic structure for f of x, and I'll show you how that works, then this is an even function. If it turns out that the f, when you replace, oh, that is not right. That should have a negative x right there, and I will make sure to correct that when you have your script. But the f of x equals the negative f of negative x, then that simply means that when you replace negative x, you got a negative value for the function. So that is when you have an odd function. So you have to identify whether your function is even or odd before you do any integration work. You have to look only at the functional level. So let's take a look at how you do that.